Welcome. Good afternoon. Let's try to dream a little bit. And but dreams are, we can dream, but of course, if we want as engineers, scientists, contribute to have more people dreaming, we have to link the dreams with some real life issues and real life problems. So this is a reason why I gave the title of my talk. It's not to say macroalgae for energy production, but can we plot the link from dream to reality? One of the starting points that we should follow is actually just to imagine. We could imagine in our world that we know now with a lot of waste, use of energy, how we could change this world in a world where we could have a switch from the one way where we extract resources, we use them, we dispose the waste, to a world where we could have a more cyclic behavior, where the use that leads to waste will include an additional step where this waste becomes new resources. So let's try to see and imagine if there's a way to work that way. And I just took this example of, I could be more aware than others, about liquid fuels. One important items in the dream and to reality is that we must find a way to address real problems. And when you look at real problems, very soon in the equation will come an important parameter, which is money. We can dream about whatever, but somehow there will be an economical parameter that will take place. So if we want to develop new solutions, for instance, for energy, it's better to look at how the people are using energy. Now they are using energy for heating houses, they are using energy in microelectronics, they are using energy in mobile systems, but they are also using energy in mobile vehicles, cars, trucks. And cars and trucks or planes are using liquid fuels. We can dream about how we could put batteries in planes, but for a while they will be using liquid fuels. So let's think about the liquid fuels and let's see how does it work. So right now the process goes with drilling, refining, selling, using, and releasing. We have CO2 that is released. You know the contribution of CO2 has a greenhouse gas because CO2 time in the atmosphere is very long, 1 century. And of course, this is the current status of our economical system. We wish it might work where after using and releasing, we could go back to some refining. So let's try to see what it means. And can we put the starting points, the first bullet about how we could develop a concept that will create the solution for this equation. And something that is very important, it's because right now, there are the major concern about the global warming, contribution of CO2, methane also, and people are ready to invest a lot of money to capture CO2. And they say, okay, let's go to capture CO2 and put it underground. And for me, it's still hiding the dust under the carpet. If we want to change our state of mind, we should look at CO2 not as a waste, but as a resource, as we should look at the other type of waste and see, can we do something with it? So this is why it's important that we can actually change it. And something to require achieving these dreams is innovation. And this is where you take place. This is where the high-tech company take place. This is where people who are willing to use their brain to change the game take place. So innovation, what is innovation? I took this from a major company, and if there are one sentence you should remember if you are interested in research and innovation, this is a sentence you should write down and maybe put it write it in stone. Innovation is a profitable money execution. We must do something and achieve it. Of strategic, it has to come with a plan. Creativity, this is where we dream. Creativity alone is not enough. Dreaming alone is not enough. Shaping the creativity in a way that will be able to follow this process with the fact that, as I said at the beginning, there will be one step coming sooner than later where the money will take place. Investments, revenues, outcomes, incomes, it's important. So another way is to define innovation like surfing. Because innovation is totally the same thing than surfing. First, you must identify the good wave before it rises. What will be the next market? What will be the next opportunities? Secondly, you must start to paddle before the wave arrives. You must be ready and in a move as the wave is coming. And thirdly, which is quite important, you try not to fall until you reach the beach, and sometimes we'll say the beach in Bahamas when you can enjoy your new status of wealthy persons because of your innovation. So this is the equation. The equation is, we know that they have CO2 emitters. And of course, I took this example. I could take the example of some other waste, okay? But let's look at it. So step one, we have CO2. At the end of the story, we wish CO2 could create energy, chemicals, heat, fuels, nutraceuticals, etc., etc. And that's the question. And part of the answer could come from macroalgae. Something that is important, and I want really to focus on it, is that it's a part of the solution. We don't have a single answer for this complex problem. We cannot say for energy, for instance, photovoltaics will be the solution. Wind turbine will be the solution. Macroalgae, just forget everything else, macroalgae will be the solution. It has to be part of a more global and integrated understanding of the problems and the combination of adapted solution. So that's how macroalgae look like. A couple of macrons, unicell, it's a single cell. And when you look at it, you see that it's very complex. If you are familiar with some biology that you did, you have the nucleus, you have different systems. And here, you have a vesicle that contains oil. This is how the macroalgae will survive when winter is coming. I mean, they will store the nutrients, transform them in oil, and be able to reuse them when they are ready to develop again. So if we look at what we have first and what we need, initially we need light, we need CO2, we need water, and nutrients. So if we want to combine water with nutrients like phosphate nitrates, we can use reclaimed water because reclaimed water has this. Macroalgae will be the micro factories that we hope will transform these sources into valuable products. livestock food, fuels, chemicals, nutraceuticals even contribute to clean water. Because if they take the phosphorus, phosphate, nitrate out of the water, it's a way to contribute to it. And energy. Just, I don't know how many chemists are here and how many students survived their chemistry course in high school or first year. So I won't put too many equations. Just to show you that this is the oil. And the oil, you can transform it with a basic reaction, well known, in something where you have actually these components now, they were connected, now they're independent. And these are contributions, they are components of the fuels, and mostly diesel, larger molecule than gas. And glycerol. Actually, a side effect of the development of macroalgae, even if it's still very small amount, well, that's the glycerol is a side product or byproduct, and because of that, the development of these new side products destroyed worldwide the glycerol facilities that were used because there's an overproduction even for the small amounts of glycerol. So let's forget about the chemistry for a while, and let's look at how the macroalgae can compete when we look at the oil they contain compared with the other vegetables. And you see that this is a graph that was given in 2007 by Kisti about what should be the expected oil production per hectare. So it could be per volume or whatever. But you see that compared with the palm oil, when you take into account the wool tree, okay, not the fruit, the wool tree, macroalgae are supposed to totally beat the other competitors out. Okay, so that's a good part of the story. So now let's have a foot back into real life. First, do we need alternative fuels? Are people expecting new fuels? So we know that fossil fuels will be here for long. Okay, it's not about tomorrow. But what we observe is that there's a global demand for these alternative fuels. And we can see actually like some example about the agencies that predict the requirements for more than 1 billion of gallons of renewable fuels. See that the US Navy wants to operate at least with 50% of non-fossil fuels by 2020, which is quite close. And aircraft companies, all the aircraft companies, they know that they won't solve their fuel problem by putting batteries in their plane. They are working on it, they have demonstrators, but all of them had already some real-life tests when they use a blend of jet fuel made from algae or other sources, blended with a reactor, an engine running across Atlantic, across Pacific, etc. So the major industry, they are looking at it. So, of course, we have to look to the competitors because there are industries that are well developed. So we could use palm oil. You know that palm oil, we could use it. But the problem is that it competes with wildlife. Okay, palm oil, maybe it's not the best solution. So what about using ethanol, corn-based ethanol? Yes, but it competes with edible culture. So our way is that to look at macroalgae, and actually macroalgae were the first components that were used by Mother Earth to make the fossil fuels, because the oil that you are drilling out, it's just made from the macroalgae that settled down and were compressed by the pressure, heat up, carbonized, and this is where all this oil and methane are coming from. They are coming already from macroalgae, but it took maybe 10,000 years or more to make this. Of course, we want to speed up the process. And they do not compete with edible culture. They do not compete with clean water or wildlife preservation. Now, let's go back, or let's go further and see how we can grow macroalgae. It's not enough just to say we can use it. How can we produce them? So a little bit of biology, and I'm not a biologist, but just to understand what is going on. The first process is photosynthesis. This is what it's named the autotrophic pathway. Photosynthesis is, you have water, you have light, you have CO2, and this will combine the reaction within the cell with the name the Calvin cycle, and that will incorporate the CO2 and produce sugars. And sugars are the fuel for the cell. But if the cell is feeling that nutrients are reduced, the cell will transform its biomass into some very easy to store component, which is oil. This is what we do when we have 3 slices of pizza instead of 1 fruit. We store the energy, okay? So we don't call it oil, we call it fat. So what we have here is the Calvin cycle. And when we look at in more details, but we don't have to go into details, what is important, 2 things I'd like to show you. First, that carbon dioxide, it's part of the cycle. This is one of the reagents that is used. But mostly look at it, this part of the Calvin cycle, it's complex. Carbon dioxide, it's a carbon with 2 oxygen. It's a hyper-rusted carbon. It's like iron oxide. That if you want to take the carbon and put it back into some organic chemistry cycle, you have to remove 2 oxygen. And these 2 oxygen actually, it's like a superoxide. And when you have an oxide, it's very stable. So you have to take the carbon which was very stabilized, very low in energy, and take it up and reduce it. And the way the cell do it is through a multi-step and complex mechanism. It's not easy, because if it was easy, we would do it by chemistry for a long time. So you've heard, maybe if you're interested, that people are claiming that they want to do artificial photosynthesis. But this is really a challenge, a very, very difficult challenge. So remember about that. The photosynthesis, it's a complex multi-step process that will take the carbon with 2 oxygen back to some organic molecule. Now, what we have the other approach, which is the heterotrophic approach. Autotrophic approach, you take carbon dioxide, you take light, you transform it into organic molecules. Heterotrophic approach, you use organic molecules that you transform with the algae into other organic molecules. So you try to use low-value organic molecules and transform them into high-value organic molecules. Because you are not dealing with CO2, you don't need light. So you can use a bioreactor, the usual bioreactors that people are using in biotechs. And the best example, and I would say the most successful story until now, is Solazyme, the American company, who has been very successful in working with USA, Europe, Brazil, Mexico, and actually what they claim, Solazyme Inc., it's from their site, they just announced that they are able to produce 450,000 tons of oil with USA and Brazil, which demonstrates that it's a major achievement, of course. And they make surfactants, they make additive cosmetic. So if we compare the 2 processes, what are the assets and drawbacks of each? Heterotrophic growth, they do not require light. Good point. They can use bioreactors that have been developed for years, so you can use major bioreactors, so you have the industry, you have the technology available. They produce high concentration biomass, which is very important, because at the end of the day, you can grow algae, but you have to take them out from the reactor, separate them from water, and this process costs money. If you come with a high concentration, you will reduce the cost downhill of your process overall. But they do not consume CO2. So you cannot use them to reduce the CO2 impact. And of course, you need cheap or free organics. So if you have sugarcane waste, for instance, that's perfect. And they work only with some specific macroalgae strains. I compare with the autotrophic growth, photosynthesis, we use a larger range of macroalgae. There are 40,000 freshwater, salted water macroalgae strains. So you can actually identify, select some of them. They will transform CO2 into organic matter, which is good, but, and probably you don't see here, they need light. It's a challenge to come with high concentration. Actually, it's very difficult, and people haven't been able to achieve it. The technology, now they are not bioreactors, they are photobioreactors, because you must provide the light in addition. It's not fully developed. So there's a lot of research or a lot of claims, and it's not a mature technology. So let's look at how you can produce algae. And of course, as any other production, it's a competition between the cost to make it and the revenue. So the first one, I call it gathering. Gathering is that just you take a lake, you let algae grow, and you just collect them. You have no control. If it's water, there's nothing, etc. It doesn't cost you a lot. It just costs you to have a lake and a collection of other system. It's cheap, no control, no efficiency. The problem with the lack of control is that if I want to produce some chemicals, so part of the, I'm focusing more or less about fuel, but we can talk about omega-3. You know about omega-3? Yes? Do you eat eggs with omega-3? No, you don't? Did you put a cream with omega-3? You know how, I mean, except for the eggs, because they feed the chicken with the omega-3 enriched food, but most of the omega-3s are made by taking the krill, the shrimps that you have in Antarctica, that the whales are feeding off. And these shrimps, so the krill, K-R-I-L-L, is rich in omega-3. So they just take a lot of it, crush it, and extract the omega-3. That's good. And after you can have some sushis. And the second part is that if you want the control, you can come to what I call agriculture. So you have more technology, like a farmer. You know, the farmer, he knows what he does, but he has to adapt to what the variation, seasonal daily variation. If it's dry, he has to water. If it's cold, he has to wait until he can put the seed, etc. So he has to adapt to variation of the environment. And there have been these systems. I will show you some closer picture of this system. It's in Israel. This is in Israel as well. And you have tubes, you have the ponds here, etc. So, but still, you must be an expert to adapt your system to the environment and how the environment changes. So the level 3 is what I call industrial. Industrial is when you control everything. If you control everything, you can plan the production. If you control everything, you can put your production line wherever you want, even in Canada. You can understand that this doesn't work in Canada. Hardly, mostly with the winter we had. So, what do we need? We need light, CO2, water, nutrients, and temperature, because we cannot produce algae at -20. Light, energy. So we need energy, but we need a free source of energy. What is the best free source of light? Sun. So let's use sunlight. That's a good idea. Yes? No? Who thinks it's a good idea? Of course, it's a trap. Let's go there. A lot of space, a lot of sun. That's perfect. Oh, no. That was a trap, but you didn't fall into it. So now it's not such a good idea for many reasons. First, we have sun in the desert, but we have no water. This is how we define it, actually. How do we bring CO2 on site? Another question. Desert is very hot during the day, but cold during the night. And algae, they don't want very cold, don't want very hot. They just need, let's say, 28, 30 degrees, that's perfect. The temperature and light are fluctuating. So that means because we are using sunlight, have you noticed that we don't have sunlight during the night? And temperature is falling, increasing, etc. It's difficult to implement a continuous process. We cannot. And okay, they are fragile ecosystems. So if we manage to destroy everything, waste everything, the lagoons, the seas, the rivers, etc. Now let's go and waste our desert. Who cares? I mean, at the end, we'll change our planets. We'll move somewhere else and to waste something else. And something which is very important. Let's say that manage to put water in this large open system. What happens in desert with the sun? That water evaporates. And another maybe information that I wish you could remember is that 1 hectare of open pond will lose 50 cubic meter of water per day per evaporation. That means that if I want to develop a real scale open pond system in the desert, every day I will lose 50,000 cubic meters of water, which is the most valuable resource in desert. So this is not the best idea. So actually, when you look at the initial idea was, let's put our system close to the free resource, sunlight. But this is not what people do in industry. They put their system close to the expensive resource, CO2, water maybe. So you have to look at where are the CO2 emitters and try to find a place to put your system near them. And the main CO2 emitters are the fossil fuels, coal, gas, power plant. Remember one number, 50,000 cubic meter water per day. Now I want you to remember another number when you listen to people talking about CO2 capture. These are the number. It's 2 million cubic meter of flue gas emitted by a single power plant per hour. A 900 megawatt power plant will release 2 million of cubic meter of gas, atmospheric pressure, per hour. 12%, so let's say 10% of it, it's CO2. So one single power plant will release 200,000 cubic meter of CO2 per hour. And this is what we are talking about. Our goal is not to come with some fancy materials to capture a tiny amount of it. Our goal is, can we deal with this huge amount? Of course, we can look at it as a resource. So the other CO2 emitters are the cement factories, because they are using a calcium carbonate and burn it and release CO2. The good thing with it, it's a pure CO2 emitter, and they emit a lot. And also, when you have biodigesters, so you take the waste and you have the batteries, you have towers, and they will produce biogas. Biogas, it's a mixture of methane and CO2. And if you burn it, you have quite a clean CO2. It's not the same level as a power plant, but in terms of cubic meter, it's a good starting point. So when you look at this, all of them are in industrial or urban locations. And I just told you we need to implement our dream close to the CO2 emitters. But the cost for the lands near cities or in industrial area, it's expensive. It's not the desert. So that tells us that if we want to dream but come with a realistic solution, we have to come with something with a small or limited footprint. A system where we won't have to put thousands and thousands of hectares of open ponds just to convert the CO2. So now, let's see from dream to reality, what could be the challenge for an industrial production? A production that will address the large volume of CO2 and, of course, produce a large volume of biomass, macroalgae biomass. We have to come with efficient conversion of CO2 into a valuable biomass. Something in addition is that if I spend money to capture the CO2 from the power plant, for instance, I don't want to waste this money and this CO2 by releasing most of the CO2 back to the atmosphere. We want to provide a 24 hours, 7-day production system to fulfill the industrial requirements. A system that would work only a couple of hours a day and take some days off. You know how we call it? France. We have, oh, yeah, okay, that came to your mind. So we want that. We want this system to be independent from any parameters that could change. Temperatures, the light, winter, summer, morning, night, north, south, etc. We want it to be independent because we want to develop a system that we could sell to anyone, of course. Because don't forget that the last step of the innovation to reach the beach and to sit on the beach and enjoy life. So we need money for that. So we want to sell that. A full control and prevent any environmental contamination. Full control means that I will optimize. I don't have time to speak about it, but some algae will produce more oil, some algae will produce omega-3, some algae will produce some surfactants, etc. And I don't want the contamination. I don't want them to be contaminated. And if I have an open system, they will be contaminated because there are algae everywhere. On the other side, I don't want to come with a very aggressive algae and this algae to contaminate the environment. So I need a closed system for that. And I want to use what I call optimized macroalgae strains. They are not genetically modified, but they can be optimized. And if I develop that, I don't want any contamination. And of course, as I say, we want a limited footprint for what I call the biofactory. So that's the industrial requirements. What should be the technical requirements based on the industrial requirements? We need to create a photobioreactor, PBR, able to work continuously and independently from daily or seasonal or geographic variation. We want to be sure that when we inject CO2, the gas, 100% of the gas we are injecting will be dissolved into water and be used by the algae. No release. We want to keep constant the optimum condition because at the end of the day, it's a biochemical reaction. We have some parameters, nutrients, temperature, water, pH, CO2, and what we want is to be able to optimize it. Now, this is also a way to optimize the system by itself. I want to provide a compatible, cost-effective design that I could scale up easily. I want to come with a continuous production mode, not a batch one. A batch is when you seed your tank or your system with some algae, you let them grow, you collect them, and you do it again. So you have to deal with another parameter. The concentration in the biomass is changing with time. And nutrients will have to be adapted. And we want to use an artificial light because we don't want to have any seasonal variation. But I cannot spend money on some energy source to produce light and collect less energy at the end of the day with my biomass. So I need to find either a cheap or optimized way of using light for what I need. So let's take some example of what we develop and to illustrate, actually. Dissolve 100% CO2. So these are the pictures I took in the previous system. I show you, so this system, it's near a power plant. You see the photos? Let's look at how much CO2 they are wasting. Initially, I was thinking they were losing 80, 90%. No, 99% of the gas that is injected just go back outside. What we did was to combine, and of course we want to come with innovative but realistic solution, to combine some commercial ceramic support and use them as a gas-liquid contactor. So we make them hydrophobic, and this is how it looks like. So you see there are commercial components. And just to show you that depending, you don't have to look at I won't explain the parameters, but just to show you that when you optimize that, you can multiply by 10 the amount of CO2 which is actually dissolved. And here you see that actually this is a time in minutes that we reach very rapidly a high level of CO2 being dissolved. We cannot dissolve as much of CO2 that you have to go back to your chemistry class in high school about the pH reaction of CO2. But just to illustrate to you how we can play with that. Now, CO2, 100% of the CO2 we are collecting that we inject in water, we dissolve it. Light, that's the sunlight spectrum from UV to infrared. This is where the algae are collecting the photons, the energy of the photons. And here, maybe you don't see them clearly. This is the blue. This is the absorption spectra. You have the blue here, and you have the red. The green algae absorb the blue and the red. Nothing else. So that means that using this energy, these photons are totally useless. They just contribute to heat my system. I don't want them. I want blue and red photons. How could I get blue and red photons? I have LEDs. They are perfect, low energy consumptions, high power, directional. I have the blue, I have the red. I can use LEDs. I forget sunlight, I forget electrical bulbs. Let's focus on LEDs. Now, I want to produce more biomass. Let's put more photons. No, it doesn't work. Because the algae, they are very fragile system. They need some light, and this is the intensity, the light intensity, and this is the growth rate. No light, they don't grow. More light, they will grow. But beyond a given light intensity, they will stop. Because this light, the photons, they don't have time to take care of them, to release them. So the photon will destroy the cell. And that's why the algae has a system, which is a small antenna most of the time, some receptors, where they say, oh, I stop collecting the photons because they will kill me. So I cannot increase the intensity the light intensity beyond one level. So this limits my system. The good thing is that the photons, I show you this complex Calvin cycle, okay? I told you this is a multi-step reaction, complex. The good thing is that this part of the cycle needs photons only during a very short time. The rest of the cycle, photons, sending photons, is useless. So what I can do is just switch on red and blue, but send light only for 1% of the time. And if I send light for 1% of the time, only 99% of the time, I don't need light. So actually now my energy cost is totally reduced. And what we did was to calculate that if we calculate the energy required to produce the light, and we just calculate the energy produced by the biomass just by burning it, okay? We don't value it. Burning it, the energy ratio is 5:1. If we put one amount of energy, we will collect 5 at the end. Yes?
So where did the rest of the energy come from?
No, this is the photons will contribute, the energy is coming from CO2. Because this converts the CO2 organic into biomass. So we look at the light cost, photons. CO2, it's free. We don't evaluate the energy production of CO2 that is combined. And we look at the final amount of biomass that is produced. Yes? No?
Well, the light the energy in the light is used to break apart the CO2.
It's part of the cycle, yes.
Where does the rest of the energy that breaks apart the CO2 come from? It's not coming from the light.
No, because actually, because it's a multi-step process, there's only a couple of steps that requires photons. But after, there will be a complete cycle that will conduct to the sugar. So if you look at the equation, I put it, but I didn't focus it on it. To make one molecule of sugar with 6 carbon, you need 6 CO2 and 48 photons. But the energy of the sugar that is produced is more than the photons alone, because you have the energy of CO2. And this is what you have where the up-to-date technology used for the open pond. Engineers. Just to prevent settling. You can imagine that this motor consumes a lot of energy. Let's take another good example of the up-to-date technology at the same place. You see here? You have a paddle, and the system is just here to steer the pond. You don't have to be an engineer to calculate that, compare with the energy production in microalgae here, the energy cost, it's 50 times higher. So I told you that what happens with autotrophic culture is that the technology is not well defined yet, which is not a problem. This is a path for opportunities. So let's try to find what should be a suitable design. And there have been people developing concept or installation with tubes, things worldwide. And you see there's a lot of design, a lot of installations. This is in Spain. This was with the MIT spin-off company who managed to drain a lot of money and just went bankrupt. There's the bags here, greenhouse. There's quite large facilities with tubes in Germany, etc. So we want to scale up our system. And the problem will be that if I'm using sunlight, the light is outside. And the light will be absorbed by water and algae. So I must create a system where the light is outside that cannot be too large, because the light will be absorbed. And the maximum size, if I'm looking for tubes, will be 10 centimeters, maximum. That hazardous light can go penetrate through maybe 5 centimeters. One tube, diameter 10 centimeters, you do the math. I want to obtain a total production volume of 100 cubic meter, which is a quite small volume. I need 12 kilometers. And this is very good if you have a tube producer. So our solution took into account all these parameters. And this is how we come from the dream to reality, because to deal with reality, you have to address the real life problem. Closed photobioreactor, complete control, industrial production. We don't use cylinders, tubes, we use tanks. Why? Because tanks you can have a large volume with a small footprint. And tanks are cheap. People know how to make tanks. The system, lighting system, has to be, we don't want to use sunlight, we have to use artificial light, but it has to be adapted to the correct wavelength. It has to be adapted to the frequency required just to initiate the photosynthesis. We don't have to send light every time, all time long. We need to be sure that CO2 we can inject that we will recover will be fully dissolved. We don't waste it. Why? Because people are getting some carbon credits for collecting CO2. If I release 98% or more from it, they will have to pay carbon tax for it. They don't want it. And we want a continuous production. We don't want a batch mode. So this is an example of 80 liters that we developed. So I have a couple of movies where it's a tank. I said 80 liters. Here, you have the CO2 injectors. You have the LEDs. Red, they are white, but the white contains a lot of blue. You have the lighting system on the top. So you can take it out, take it in. I will show you another short movie. And you have a system to steer it. Another view of it, it's more stable. So you see that here you have the light inside. If I have the light inside, I can increase the size of my system. I don't have any limits anymore. Here, you have what I showed, the CO2 injectors. That means that this is a contactor. We have a better view after. This is a 4 grams per liter concentration. And you see with 4 grams per liter, which is not enough, you still have a strong absorption. CO2 injectors, where actually the water is coming through it, and we have the CO2 being injected from the outside, so you have the circulation, so we can enrich in CO2. So now, let's try to dream a little bit. I mean, it won't be a dream if you give me $2 million about how a system would look like. I told you 100 cubic meters, it's 10 kilometers, 12 kilometers of tubes. This is 25 cubic meter. So to achieve that, and it is 4-meter diameters, you have 100 cubic meters just with 4 tanks. And this is how the system can look like, where you have these photobioreactors, you see, with a system model of lighting systems inside, CO2 being sent here with enrich, different system, usual industrial tanks, production of biomass now that is collect, and sent to a system because to help to collect, to produce more oil, you must age the algae. So you have another system where you will have the aging step. to have increased the oil content. And after you process, that means you separate the biomass from water, you re-inject the water, etc., etc. So this looks very boring, which would be the dream, to come with boring industrial platforms. That means that boring industrial platforms are industrial platforms that people can work with. Now, one more thing. If we want to be cost effective, we need a high production, high concentration production. One, the open ponds, 0.3 grams per liter. The closed photobioreactors, the tubes, 3 grams per liter. We need, if we deal with that, the extraction, processing extraction of the biomass, the cost will be up to 40% overall of the cost. That means you want to reduce your industrial cost and increase your outcomes, reduce your cost, you have to come with a system where you can actually gather the biomass. And the best way is to come with higher concentration, and you need 40 to 100 grams per liter. 100 grams per liter, now you can calculate actually the volume of a cell. I mean, you don't have to do that. A macroalgae contains 85% of water. So you calculate in a given volume how much of organic you have, and this is 100 grams per liter. So you cannot have more, because algae itself contains a lot of water. And we cannot produce this by the photosynthetic process, because that will absorb light. These concentrations are almost achieved by the biotech process, the heterotrophic process. So the question is, of course, can we harvest this? And yes, we can do that. But this is where I won't tell you how. You want to know? Write a check. So, just to conclude, the question is, can we dream? And that's important because most of you are students. Part of us, we are researchers. We are here to dream and to come with new ideas, new concepts. Part of it, we don't care if they are useful or not, okay? It's not our job. Our job is part of our job is to be creative. And this is how the big discoveries were made. But when we dream, we want also to be sure that this could happen. So let's take an example of the first plane. There's a fight between American and French, but French, we know that we are the discoverers. Clément Ader, in 1890, made the first flying plane who flew for 50 meters, I think. In parallel, it was in USA, there was a competitors. One passenger. 1890. 1 century after. 100 years is nothing. Airbus A380, more than 800 passengers. The time here, 2007, it's a commercial flight. The first flight with paying passengers. From this to that, only 100 years. So if we want to come with the new solutions, and actually they are not the new solutions for next centuries. They are the new solutions for the next 10 years. In this area, in other areas. And there can be the solution if we look at the dream and if we look at the real life too. So why dreaming about new solution? Because actually, there's nothing more funny and worse to being lived. I thank you for your attention.
Let's open the floor for some questions.
Yeah.
When you have extracted what you want from the biomass, so how are you going to deal with this
Yeah.
wasted biomass?
So the question is, when we collect the biomass, how we we do the processing to separate the different components, kind of. So first, to collect the biomass, it's their very well-known system with filter press filters, to extract, or even centrifuge, and you can do that. After you have this paste, and the industry, they knows how to separate the components from large volumes. They do some separative chromatography that can deal with the large volumes, means hundreds of kilos. So this is not a problem. I don't know how to do it, but they know how to do it. Now, when you discuss, as I did, with people in chemical industry, and this is maybe another number that you could have in mind if you are interested in this domain, they are ready to pay 40 cents a kilo of biomass, weight biomass. So now you look at the process, production process, and you look at how much it would cost to just collect, separate the biomass. And if it costs more than 40 cents, you're dead. Yep.
I really missed some of your calculations. If this microalgae is purpose only for extract oil, this is for energy, or is it for the high value products?
Yeah. So, what the algae can be used for? One, what happens right now? Initially, their goal was to produce fuels, and mostly diesel and jet fuels, because the algae have this type of alkane that fits well with either the diesel or the jet fuel. So the asset of the algae is that they can really generate, some algae can have up to 70% of their dry mass in oil when you make them actually starving, and they will start to store it. The other part, which is where the chemical industry is more interested, or cosmetic, like DuPont, like Solvay, like the other peoples, is that surfactants and nutraceuticals. So for instance, they can be used for fish feeding, because they have everything good. They have vitamins, proteins. They what the fish can live on. So right now, the trend for the industry, when you look at, and I mean, if you're interested with the real market, you can go and see what Solarzyme is doing. It's mostly targeting this small market, but still, they're talking about thousands of tons.
If you calculate that, then in the end, you make a profit. Otherwise, I cannot understand. See, if you put artificial light, this is the energy.
Yep.
And in the end, the form transform it into oil and then burn out. You cannot give up more energy than.
Yes. If you use some light, continuous light, you will consume more energy, cost you more than the energy you are producing. Now, if you adapt the light to the needs for the algae, actually the amount of the videos I show with the light here, the LEDs, that seems to be continuously working, which is not. The only difference is that they are pulsing so fast that you don't see it. Okay? And actually, when you calculate and optimize it, then, I mean, I will let you do your homework as I did it, based on it. When you do it, you just come with the fact that you need light for only less than 1% of the time. So 99% of the time, algae are in the dark, but you don't see it. And because you optimize the type of photon you're producing by the LEDs, which are also cost-effective light producers, emitters, you reduce your cost. And the calculation we did was taking into account everything, including the separation process, and just calculating the energy by burning the biomass, we came with this 5-to-1 ratio. Yeah.
So just to follow up on that, when you burn the biomass, you end up with CO2 again.
Yeah.
So you had mentioned earlier that the energy was coming, The extra energy was coming from the CO2.
Yeah.
But if you end up back with the CO2, you haven't.
Yeah, but when you burn it, there's a heat which is freed. So what happens that you had CO2. CO2 doesn't burn. Due to the synthesis and photosynthesis and some light, you reduce the CO2 into carbon. And when you burn it, you oxidize.
Yeah, you're coming back to the CO2.
You're coming back. I'm not talking.
All the energy comes from the light, then, doesn't it?
No, the energy comes from the oxygen combined with the carbon that burns and releases heat and CO2. If you look at where the energy at the end is coming when you just burn it. You have a reaction which is carbon plus oxygen gives CO2. One reaction will release energy. This is when you burn. The other way doesn't release energy. You need energy. To go back, you need photons and photosynthesis. CO2 gives oxygen plus carbon, you need photosynthesis.
Is all the energy is coming from the photons?
No, part of it. The photons help the different biomolecules to reduce the CO2. It's a biochemical process. So it's not a balance because you would have a balanced reaction. So one, you have to take the energy of CO2, which is low, very stable, back to the carbon. And you need the photosynthesis for that. And you need a small burst of energy, the photons. But the photons are here to help the intermediates to reduce the CO2. So you don't have a direct balance between the energy, the photon energy, and the energy of the mass at the end, of the biomass when you burn it. So that's why it's positive. Yeah?
You might have talked about this and I missed it. You must have done this overall calculation of what's included, how much energy, how much cost, and what are the payback periods, and at the end of the reaction, how much energy came out of it, how much value add came out of it, and some kind of both a modeling in terms of both financial modeling as well as energy input and output. Is it net generator or is it net energy consumption?
When you now, the number I gave was, as I said, it was a basic number regarding, let's say we just burn the biomass and we calculate the energy, which is not the best way to for instance, to use omega-3. When you look at the heterotrophic process, actually they are using sugars and making high-value products. So now, if I understand your question, the components in the economical evaluation has to take into account the value of the product you are producing. That was your question?
Well, let me rephrase it. So you mentioned a couple of times that if you are given $2 million, you'll be able to take this energy technology further. So I assume you're in a phase of looking for capital, capital?
Oh, that's it's not the type of discussion I would have here. That's a type of discussion that I could have somewhere else.
Well, I'm quite interested to know more about it.
Okay, we can discuss later on.
Sure.
Okay. Yes?
So when you're cultivating the algae and you scale up the system, how sustainable are the other inputs like nitrogen, phosphorus, micronutrients?
Yeah.
Is that expensive?
So, and I made, of course, I made the whole story more simple than it is. So a major component is nitrate and, let's say, nitrogen and phosphorus. And you need to find it. So a good way to find it is, for instance, to use manure from agriculture because they have it. So reclaimed water, they have phosphate, nitrate, that people try to get rid of. And with the livestock waste, you can use it. So it's a combination actually where you could have it. A good thing also, I mean, what we think a good thing is that with a closed system, you are not wasting water, which becomes very important. So what you have is just to feed it with some measures that is optimized. Now, something that people have done and observed is that, of course, you need, let's say, you need carbon from CO2, you need nitrogen, you need phosphorus, but you need a lot of small stuff, small components, and they are very important. And when you look at the nutrient solutions that are made when you grow algae in the Canadian library, here, Macroalgae library, the solutions, they have a lot of additional elements, small elements. And what they observe is when you deal with, let's say, raw CO2 from power plants or cement factories, this flue gas contains these small elements. And actually, it's better to grow the algae with almost the raw gas than a pure CO2 from a cylinder. But yes, this is part of the equation, but we have a way to combine it with reclaimed water, actually. Yep.
Just last try to see to understand the energy balance. The photon is a form of energy. It's a form of energy.
Yep.
And then that was used to reduce CO2 into carbon molecule. The carbon molecule later will be oxidized together with oxygen and release energy. Carbon dioxide become carbon dioxide again.
Mm-hmm.
So the net energy, see this the form of the energy as a photon, it will be greater than the energy produced when carbon burned with oxygen released.
What? Yeah, I'm not sure if I understand perfectly your question. What I can say, and maybe we can discuss further on it, what I can say is we never produce energy. Nobody produces energy. We just convert energy. And we convert energy in ways that we can use it. For instance, in batteries, we have energy that we can transport with us in our cell phones, in this remote control, etc. Now, when I look at the market, to fuel a truck or a car, solar panels, that means using diluted energy, it's not very important. It's not very useful. I can do it. There are cars demonstrators, but I need a high density energy, which is good for liquid. So that's why I can do that. And I know I don't fully answer your question, but it's a way to convert some diluted energy into a high concentration energy. Now you could tell me, yeah, it works with sunlight, not with the LED you are using, but the LEDs you are using. But in the process of increasing, so we don't just convert, it's not carbon to carbon. What we do, we take the fundamental level of CO2 to a higher energy level of carbon. And this is where you have the energy gap. And to do that, the cell does it the best way until now, which is called photosynthesis. So they can do it with a minimum cost of energy. If we want to do it with a chemical process, now things are much more difficult. And I could say that until now, for the chemical process I know, because I'm a chemist, people are looking for catalysts to do that. This is what catalysts do, actually, to boost a reaction that shouldn't happen, because locally, at a given step, they will be able to put the molecules in the different shapes that allow them to shift to a higher energy level or another level. That's the trick. And that's what the photosynthesis does.
So when you say the 5-to-1 ratio, you mean 5 units of energy from the LEDs to 1 unit of energy?
No.
You mean the other way around?
Yes, yes.
1 unit. So, okay, so it's going to be 5, if you look at all the energy inputs and all the outputs, they're going to be even, like you just said.
No, I mean, when I say 1, that means we evaluated the energy cost for pumps, for when you extract, etc., everything. Of all the work process, not only the production, but the processing, etc. Overall, what it would cost in energy, and you come to 1. And when you calculate how much energy stored in the biomass is produced, you come to 5.
So where is the
rest of that energy coming from, is basically the question.
You are generating energy. You are generating potential energy stored in the biomass. This is what the trees are doing every day. No, you don't agree.
We're just confused.
Not this way.
What you have? I mean,
No energy can be created. The energy is always balanced.
yeah.
So these come from
Because
efficiency is
yes,
not 100%.
yeah.
Also lost energy.
Because what you have here is that, and I mean, maybe if you agree, and I'm ready to have this discussion, but maybe we can officially let this other persons maybe leave, and we can have this discussion. If I'm very happy with that. So if it's okay with you, we can leave. But you are welcome to stay.
As Eric said, you're welcome to stay and one discussions, but let's join me in thanking Eric again for this wise lecture.
Yeah.
And stay tuned
Thank
for
you.
our next one.
Thank you.